Okay, I think we'll get started. Hopefully people will trickle in. So next up, we have Anna Seigal from Harvard University, and she'll be talking to us about groups and symmetries and statistical models.
All right, so hi everyone. Thanks a lot for the introduction and for inviting me to speak. It's great to be able to give this talk today, and thank you all for coming. I take it everyone can hear me okay and can see my screen and everything. So please interrupt if that's not the case. And also please interrupt throughout the talk if you have any questions at any point. I'm very happy to take questions at any time. All right, so today I'm going to be talking about groups and symmetries in statistical models. So firstly, what do I mean by this? Well, okay, groups and symmetries motivate many statistical ideas. So maybe the most prevalent is the idea of samples that are independent and identically distributed, or IID. And this means that if we permute these observations, this doesn't change their distribution. And we can think of this as being invariant under the group of permutation matrices, or under the symmetric group. So that's maybe the first example, and then a few others that are a bit closer to what I'm going to talk about today. So there's the idea of a group symmetry model as studied in these two papers here of Anderson and Madsen, invariant normal models and invariant normal models of recursive graphical Markov structure. Okay, so these are particular statistical models consisting of covariance matrices that are invariant under a fixed group. Okay, I wanted to include this excerpt here from the paper of Madsen, which says that this smoothing or averaging mapping, which may be familiar to some of you from other contexts, is fundamental for likelihood inference for group symmetry models. All right, so that's an example of models that we want to be invariant under a group. And we can also consider what's known as a transformation family, as studied in this paper here of Dries, McCoont, and Zwiernik, which is a statistical model on which a group acts transitively. So points in the model can then be parameterized by a group element. Okay, so groups and symmetries motivate statistical ideas, and the outline for my talk is that groups and symmetries continue to motivate statistical ideas in my own work and joint work with collaborators. So I'll tell you about Gaussian group models. So that's based on joint work with Carlos Amendola, Kathleen Cohen, and Philip Reichenbach, which references this paper here, invariant theory and scaling algorithms for maximum likelihood estimation. And I'll also tell you about follow-up work on what we call DAG models, which is based on this preprint here on symmetries in directed Gaussian graphical models, and this is based on joint work with, or this is joint work with Izu Makam and Philip Reichenbach again. And throughout the talk, the focus will be on maximum likelihood estimation in these models and how we can use the group or symmetry structure to help us with this optimization problem. Okay, so there's been a few talks that have mentioned some connections to statistics, but to not assume any statistical prerequisites, let me tell you about the setup. So we have a statistical model, which I'll call M, and we're looking for the point in M that's most consistent with some observed data. So here's a picture of the setup. We have our model here, and then we have some observed data. And we're looking for the point in the model that's closest to the data in some sense. And more specifically, the maximum likelihood estimate, or MLE, is a point in the model that maximizes the likelihood of observing the data. So maybe for this cartoon picture here, this is the maximum likelihood estimate. Okay, and I said that I'd be talking about Gaussian group models and RDAG models, and I'd like to tell you some other statistical models first that they stem from, which are DAG models. Okay, so I start with a directed acyclic graph, or a DAG, which I'll call G, and it has M nodes. So here's an example where M is equal to 4. So I've got these 4 random variables here and edges between certain pairs of them. And then the DAG model associated to this graph is given by the linear equation x equals lambda x plus epsilon, where the matrix lambda has the sparsity pattern given by the DAG. So the entry lambda j is 0 unless there's an edge from j to I in the graph. Okay, and epsilon is a noise term that makes the whole thing random. Okay, so x in this example here is a vector of length 4, and that's our random vector. And we know that the coordinates of this vector should relate according to the structure of this graph. And we can imagine that the edges encode some kind of causal relationship between the variables. So that maybe lambda 2,1 measures the causal effect of x1 on x2, but they needn't be given a causal interpretation. Okay, and I'll assume that the noise term epsilon is normally distributed with mean 0 and variance omega, where the matrix omega is diagonal. So that reflects the independence of the errors. Okay, now a graph G is called transitive if whenever there's an edge from K to J and another from J to I, then together these imply that there's an edge from K to I. So for example, this graph here is not transitive because there's an edge from x1 to x3 and another one from x3 to x4, but there's not a direct edge from x1 to x4. But if we added in this directed edge, then this would be a transitive DAG. Okay, and if DAG G is transitive, then such a model, so such a multivariate Gaussian model, is firstly an example of a Gaussian group model, and secondly also an example of an RDAG model. So we can think of these DAG models, which are very popular in statistical applications, as being the starting point for the two other families of models. Okay, and the random vector x is multivariate Gaussian with mean 0, and all the information about the graph and the variances is captured in its concentration matrix, or the inverse of its covariance matrix. And the concentration matrix takes this form. So psi is equal to the identity minus lambda transpose times omega inverse times the identity minus lambda. Okay, so that packages together this lambda here from the structural equation and this omega here from the variance of the errors. Okay, so this is a multivariate Gaussian model. So it has this familiar probability density function, which I've parameterized in terms of the concentration matrix rather than the covariance matrix, but is otherwise, well, is anyway familiar. So this reflects the fact that a mean 0 multivariate Gaussian model is a subset of the positive definite cone. So this is the space in which the model lives. It's the positive definite cone, or a cartoon depiction of it. And the model is some subset of the cone, where we identify the probability density function with the concentration matrix that parameterizes it. Okay, and the positive definite cone looks more like this. So this is a slice of the positive definite cone in the space of 3 by 3 symmetric matrices. Okay, and then we're looking at certain models or certain subsets or sub-varieties of the positive definite cone. And for example, we could consider those psi that factor according to this form that we saw before with the DAG model. So where we can parameterize the psi in terms of some matrix lambda with some sparsity and matrix omega that may be diagonal. Okay, so that's one possible collection of matrices psi that we could consider. So now I'll tell you about another possibility, which is a Gaussian group model. Okay, so we fix a group.
Yeah, I have a question.
Yes, please.
Yeah, I was just wondering, in this model, what exactly is it that you don't know? You don't know the variances?
Yeah, thanks a lot. Okay, so that's a great question. So there are various situations in which various things could be known or unknown, but for my purposes, we know the sparsity pattern on the graph. So we know the sparsity of the matrix lambda, but we don't know the entries of lambda. So we know where the edges are in the graph, but not their weights. And we know that the matrix omega is diagonal, but we don't know its diagonal entries. So we don't know the variances on the errors.
Thank you.
Yeah, thanks a lot for the question. Any other questions? Okay, great. So Gaussian group models, we start with a group G of m by m real invertible matrices. And then we can define the Gaussian group model given by the group G. And this is the set of concentration matrices, which I'll call MG, which are of the form G transpose G, where G is an element of the group. Okay, so for various groups of real invertible matrices, we can construct Gaussian group models. But there are also some statistical models that already have this form. So I already said one example is that of a transitive DAG. And okay, if we know it's a Gaussian group model, what's the group? Well, the group is this set of matrices. So invertible matrices G, where Gij is 0, if I is not equal to j and there's no edge from j to I in the graph. So we can check that the condition for this set of matrices to be a group is exactly the same as the transitive condition I mentioned before. Another example, which we'll see a bit more about later, are certain RDAG models, specifically transitive RDAGs, for which something called the butterfly criterion holds, which actually I won't even tell you what that is later. So that will just be a mystery for the purpose of this talk. And the set of matrices in this case, okay, is the something a bit more complicated. So a similarly defined collection of matrices with some sparsity and some other conditions. Okay, and another example of Gaussian group models are the matrix and tensor normal models that Akshay was talking about yesterday. All right. So then how do we do maximum likelihood estimation in these models? Okay, so the model M is a set of concentration matrices in the positive definite cone. We're looking for the point in the model most consistent with some observed data. And I said before that the MLE is the point or a point that maximizes the likelihood of observing the data. So since we're in this multivariate Gaussian setting, let's say we have an m-dimensional Gaussian, then our data samples y1 up to yn, and the likelihood function is given by the product of the densities evaluated at the samples, because they're assumed to be independent. Okay, we can rewrite the likelihood like this, and this helps us to see that maximizing the likelihood is equivalent to maximizing this function here. So log deb psi minus the trace of psi sy, where sy is the sample covariance matrix. Okay, so all our attention will now be focused on maximizing this function, and an MLE given some sample data y is psi that maximizes the likelihood as we range over those psi that lie in our model. Okay, so we are looking to maximize this function over our model, so over the points that lie in our set of interest. And as we attempt to do this, there are various possibilities for what might happen. So the first possibility is that the likelihood is unbounded from above. Conversely, the log likelihood could be bounded from above, or even better, it could be bounded and attain its bound. So then a maximum is an MLE, and so the MLE exists. And the best case scenario, the MLE could exist and be unique. So it attains its maximum at a unique point. Okay, so in order to connect these notions to some properties of groups, I will motivate that just by looking at a particular familiar example of permutation matrices. Okay, so here we have some 3x3 permutation matrices. They permute coordinates. So in this case, in R3. So for example, applying this matrix, this vector swaps the first two entries. And the orbit of a point onto this group is all possible permutations of the entries of the vector. Okay, now the invariants are the functions that are constant on the orbits. And in this case, we can check that some of the invariants are these three polynomials. So the sum of the coordinates, the sum of the pairwise products, and the triple product. Okay, but in fact, these aren't just some invariants. So these polynomials generate the ring of invariants. And in this particular case, there's this nice correspondence that 2 points are in the same orbit if and only if their invariants agree. So if we want to check if 2 points are in the same orbit, we need to check all of their invariants, but actually we just need to check the generators. So we just evaluate these three polynomials and see if they give the same answer. But the problem with this as the way to test if 2 points are in the same orbit more generally is that this reverse implication doesn't hold in general. So this will only hold for closed orbits. We could have a pair of points whose invariants all agree, but they're not in the same orbit. Okay, so that's a motivation for notions of stability. So now we have a group G that acts linearly on some space V. Our orbit is the set of points we can reach, starting at some point V. So here's the picture here. Hit this red square is our space V. We have our point V and its orbit. So the set of all points we can reach starting at V. And the capacity is the infimum as we range over the group of the distance of G dot V to the origin. So in this picture here, the capacity is this distance here. Since this is the closest point in the orbit to the origin, we have that the capacity is this distance or this distance squared. All right, so now based on the capacity, we can make various definitions. So we say that a point is unstable if the capacity is 0. And the set of all unstable points is the null cone. So this is the set of points where all homogeneous polynomials that are invariants vanish. Conversely, a point is semi-stable if its capacity is strictly positive. So equivalently, if the origin is not in the orbit closure. Okay, and now point is called polystable, this stronger condition than semi-stable, if the point is non-zero and the orbit is closed. Okay, so we can see why this implies semi-stability. And then the strongest condition is that a point is not only polystable, but its stabilizer. So the set of group elements that fix the point is finite. All right, so on the previous slide, I gave an example of a finite group. So there we're either in case A or case D. So once you're not unstable, you're already stable because the group is finite. So the orbit is a finite set of points. So it's closed, and the stabilizer is a subgroup of the group. So it's finite. But for other groups and other spaces, various other things can happen. So we can imagine what happens if we act on Cm under the special linear group. Or maybe the first interesting example, we can look at the action on rectangular matrices of size m1 by m2 by multiplying on the left by matrix in SLM1 and on the right by a matrix in SLM2. Okay, so why have I told you about all these notions of stability and also all these properties of the likelihood function? So the main point of the first half of this talk is to tell you about these connections between invariant theory and maximum likelihood estimation. So between these two pictures here, this picture of a point and its orbit in some space, and this picture of a statistical model and some data. Okay, so for this left-hand picture here, we had these 4 notions of stability, and on the right-hand picture here, we have these possibilities for what could happen to the likelihood function, so that it could be unbounded or bounded, or the MLE could exist, or it could exist uniquely. And I will tell you about the correspondence that holds between these properties here and these properties here. Roughly speaking, the strongest results that we have are situations where there's an exact correspondence. So unstable corresponds to unboundedness of the likelihood, semi-stable corresponds to boundedness, polystable corresponds to MLE existence, and stable to unique existence of the MLE. And I'll tell you about this correspondence in the setting of some Gaussian group models, but the correspondence also applies to log linear models, which is something that we explored in this paper, toric invariant theory for maximum likelihood estimation in log linear models. Okay, so log linear structures also appeared earlier today at this workshop in Jonathan's talk in the context of maximum entropy. And this is where they appear. All right, so then back to the Gaussian setting. We have a group of real matrices, and the Gaussian group model MG is a set of matrices G transpose G, where G is in the group. Okay, so then this is our theorem for reductive groups. So these are the correspondences that hold in the setting of a Gaussian group model defined for a reductive group G. So a point is unstable if and only if the likelihood is unbounded from above. It's semi-stable if and only if the likelihood is bounded. It's polystable if and only if the MLE exists. And we have a forwards implication in this last case here that the stability of a point implies that it has finitely many MLEs, and in fact just a unique one. Okay, so why does this theorem hold? Before I get to that, the stability is not under the group itself, but rather under its intersection with the special linear group, or the matrices in the group that have determinant 1. And this is all in the setting of real matrices, which is more relevant in most statistical applications. But there's also an analogous complex setting. And in that complex setting, in fact, we have equivalents of all 4 of these conditions. Okay, so now I'll tell you something about the proof idea. Well, the log likelihood function, as I mentioned before, is log det psi minus the base of psi sy. And we know that our matrix, our concentration matrix psi, because it's in the model, has the form G transpose G. So we can write our log likelihood, in fact, as a function of our group element G. And this is what it looks like. So it's log det of G transpose G minus 1 over n, the norm of G dot y, where y is our sample data. Okay, so now we can see quite a close connection between maximizing the likelihood and minimizing this norm here, which is the capacity. Okay, and this connection between the notions of stability and the properties of the likelihood allow us to use geodesically convex algorithms for norm minimization over the orbit to find the MLE. So such techniques are looked at in these 2 papers here. This one of Bergesser, Frank, Skag, Oliveira, Walter, and Wigderson, many of whom are participating in this week's workshop. And even more specific to this workshop, this paper of Frank, Oliveira, Ramachandran, and Walter, which gives near optimal sample complexity for matrix and tensor normal models via geodesic convexity, and which, yeah, as I said, Akshay discussed yesterday. Okay, and what about for non-reductive groups? Well, in this case, we know slightly less about the connections between stability and the structure of the likelihood, but we can show the if and only if conditions for unstable and semi-stable, and a forwards implication that a point being polystable implies that its MLE exists. So in comparison to the reductive case, we lose the reverse implication here, and we totally lose the relationship between the stability of a point and the uniqueness of its MLE in general. Okay, all right, so I'd now like to go back to DAG models. Okay, so this is the slide I went through before with this DAG and the DAG model that we define on it. So, okay, I've talked about Gaussian group models, of which this situation is a special case when the graph is transitive. So what about RDAG models? Okay, well, I'll start with an example. So I'll fix the DAG G, where, okay, I've dropped the x's. So now we have edges from 3 to 1 and from 3 to 2. Now, the DAG model on this graph consists of concentration matrices, psi of the form given in terms of identity matrix and lambda and omega, like this, where the sparsity condition on lambda says that lambda ij is 0 unless there's an edge from j to I in the graph. Okay, so what does that mean in this example? Well, lambda has to look like this. So all entries are 0 apart from the 1, 3 entry, because that corresponds to the 3, 1 edge, and the 2, 3 entry, and that corresponds to the 3, 2 edge. Okay, so lambda looks like this for some unknown values of lambda 1 and lambda 2, and omega is some diagonal matrix, which is positive definite. So we have some unknowns, omega 1, omega 2, and omega 3. That must be some positive real numbers on the diagonal. Okay, so that's the DAG model for this graph. Now, in our DAG model, we define on a DAG together with a choice of coloring, which I'll call C, of its vertices and edges. Okay, so for example, here is such a graph. So it's the same, it has the same adjacency structure as this one here, but now each of the vertices and edges has been assigned a color. So 1 and 2 are both blue, vertex 3 is black, and the 2 edges are red. Okay, now what does the RDAG model on this colored graph look like? Well, it's parameterized by a matrix lambda, which has the same sparsity pattern as the uncolored case. But now, because the 2 edges have the same color, the entries lambda have to both be the same. So these 2 parameters here are replaced by this single parameter lambda. And in the matrix omega, we do something similar. So if the colors are the same, then the values have to be the same. So vertices 1 and 2 have the same color, so that means that their variances, i.e. the first entry on the diagonal and the second entry on the diagonal, have to take the same value. Okay, so the RDAG model has taken what was this 5-dimensional model and replaced it by this model with only 3 parameters, just lambda and omega prime. Okay, so now I'll tell you the definition in generality. So we fix a DAG G with a coloring C of its vertices and edges. Okay, so on the previous slide, I showed that example. The RDAG model on the pair G with C is the set of concentration matrices, which take this form, that satisfy the following conditions. So lambda I has to be 0 unless there's an edge from j to I. Lambda ij has to equal lambda kl whenever the edges from j to I and from L to K have the same color. And omega ii has to equal omega jj whenever vertices I and j have the same color. Okay, so that applying that procedure to this example here recovers these 2 3x3 matrices that parameterize the RDAG model. Okay, so how do these models generalize usual DAG models? Well, if we just give each vertex and edge a unique color, then conditions 2 and 3 don't do anything, and we just have this condition on the sparsity of lambda. So that's the usual DAG setting. So that's one hypothetical question and its answer. Why do we call them RDAGs? Well, they're inspired by their undirected analogs, which are called RCON models, as studied in this paper of Huysgaard and Lauritsen, called graphical Gaussian models with edge and vertex symmetries. And the R stands are restricted because adding the colors imposes restrictions on the model. Okay, and I will tell you about some of our results that hold for RDAGs, and throughout, I'll have to assume what we call a compatible coloring. So what this means is that if the edges from J to I and from L to K have the same color, then the vertices I and K also have to have the same color. So we impose that the child vertices I and K have the same color, but not we don't have this assumption on the parents. Okay, and it's an open problem to extend our findings to the setting of a non-compatible coloring. Okay, so I said I was going to focus on maximum likelihood estimation throughout this talk. So what does maximum likelihood estimation look like for these RDAG models? Well, it's linear algebra. And okay, if it's linear algebra, it involves some matrices. So what are the matrices involved? We have our data matrix Y. So here, perhaps unusually, each row of the matrix corresponds to one of the nodes in the graph. So one of our scalar random variables, and each column is a sample. Okay, so that's the matrix that we start with, and from that matrix we build what we call augmented sample matrices, which we denote by MYS, one for each vertex color S. Okay, so we're going to use this matrix here to build some bigger matrices. And what does the process look like? Well, the RDAG model.
Got an email that says
Is there a question? Okay, feel free to interrupt again if anyone has a question. All right, so here's an example of an RDAG model on 7 vertices. So vertices 1 and 2 are both blue, and the other vertices are 3 through 7 are black, and each edge has also a color assigned to it. So in this case, the matrix Y would have 7 rows, and we build from the matrix Y this matrix MY blue. So for each vertex color, this example just shows what happens for the blue vertex color. Okay, so how is this matrix constructed? Well, the first row of the matrix is labeled by the blue vertex color, and there we have the sample rows Y1 and Y2 corresponding to the 2 vertices 1 and 2 that are blue. And then each subsequent row of the matrix is labeled by an edge color, and the entry of the matrix tells us the vertices that are the sources for an edge of that color. So for example, for the red edge, we see we have a Y3 here that reflects the fact that there's a red edge from 3 to 1, and there's a 0 here because there's no red edges that have as destination, as target vertex 2. Okay, and similarly, there's no orange edges that point to 1. So this is a 0, but there's 3 that point to 2. Namely, they come from vertex 3, vertex 5, and vertex 6. So that's why we have Y3 plus Y5 plus Y6. And okay, I'll maybe spare you the other rows of this matrix, but there's some combinatorial procedure that takes us from a graph to these augmented sample matrices, one for each vertex color. Okay, so here's our example. And then the existence of the maximum likelihood estimate is captured by doing some linear algebra on these augmented sample matrices. Okay, so here's our result. We have that the likelihood is unbounded from above if and only if the 0th row, so the top row of this matrix, is contained in the span of the other rows for some vertex color. Conversely, the likelihood is bounded from above if and only if the MLE exists, which happens if the top row is not in the span of the other rows. Okay, and the MLE exists uniquely if and only if this matrix has full rank for all vertex colors. Okay, and we can also use this line of reasoning to give an algorithm to compute the MLE. So this is the algorithm. So for each vertex color, S, you project the top row onto the span of the others to get its projection, which I'll call PYS. Then the maximum likelihood estimate in the entries of the matrix lambda, so our best guesses for each entry of lambda, are the coefficients that write this projection as a linear combination of the other rows of the matrix. And our MLE in the omega coordinates is given by this formula here. So it's the distance from the projection to the top row of MYS squared, and we divide by alpha S. So alpha S is just the number of vertices of color S. Okay, so we can see that linear algebra, once we've constructed these augmented sample matrices, captures the existence of the MLE and also an algorithm for how to find it. Okay, so I will.
There's a question.
Yes.
You mentioned that this RDAG model generalizes the regular one if you make everything unique, right?
Yes.
What are these like what do these set of matrices look like when everything's unique?
Great. Yeah, thanks a lot. Thanks a lot for the question. So I will tell you. So when all the when all of the colors are only used once, so when every vertex has a unique color and every edge has a unique color, this construction here, let's see, well, it will just have one column because we only have one vertex of that color. And then beneath it, we will just have the sample vectors at the parents of that vertex. Does that make sense? So in the usual DAG case, each of our augmented sample matrices are actually just a submatrix of the original data matrix, where the top row is the child node and each of the other rows are its parents. All right, hopefully that answers your question. And this theorem is a generalization of what we know for usual DAG models. So in that case, we have the okay, hopefully you can still see my screen. In that case, we have the condition that the child node is not in the span of the vectors at its parents, is equivalent to the existence of the MLE, and similarly, the uniqueness is given by the full row rank of each of these submatrices, given by a child node and its parents. All right, thanks for the question. Any other questions at this point? Okay, so I will finish up by connecting this back to looking at groups and stability. So I mentioned before that the group associated to an RDAG model is this set of matrices here. So we consider those invertible matrices where the entry Gij is 0 if I is not equal to j and there's no edge from j to I, and such that Gij is equal to gkl whenever the edges from j to I and l to k have the same color, and when the diagonal entry gii equals gkk whenever the vertices I and k have the same color. Okay, so we can ask, when is this set of matrices a group? So this is a question that we asked ourselves in the course of doing this project, and the condition that we obtained is that the graph is transitive, and this condition of the butterfly criterion holds. Okay, but unfortunately, this group is not reductive, apart from in very special cases. So we don't have the strongest statement of our correspondence between stability and the likelihood. We only have the weaker correspondence. Okay. However, we can actually show that for an RDAG model on the graph G with the coloring C, where G is transitive with the butterfly criterion, and if Y is our sample matrix, then in this case we have this full correspondence between these notions of stability and these properties of the likelihood function. Okay, so in this special case, although the group is not reductive, we were able to get this full correspondence. And in fact, there's a sense in which this theorem holds even when this set of matrices is not a group. So when this transitivity condition and the condition on the coloring does not hold. But I won't say anything more about that now, because that's all I want to say. Thanks a lot for your attention.
All right, wonderful. Are there any questions? Oh,
Hi, Anna. What is the butterfly criterion? It's very curious.
Yes. So the butterfly criterion looks at you take a pair of edges in the graph that have the same color, and you look at all of the. You'll see that there's a reason why I didn't try to explain what this is in the talk. Okay, so you have your pair of edges of the same color, and then you look at all the paths of length 2. So you start at the source for one of your edges, you go to a different vertex, and then you come back to the target. So that's a subgraph with colors still assigned to each of the edges. And the condition is that those two graphs should be isomorphic, so the same after relabeling the vertices. That's the criterion. So it's it was interesting to us that it's not the condition that the whole subgraph on a pair of vertices is isomorphic. It's something a bit weaker than that. So we give an example in the paper where we don't have the isomorphic property, but we have the butterfly criterion, and the set of matrices does form a group.
oh, we have another question.
Thanks for the talk, by the way. But one thing I was wondering about, I seem to remember that, if you're trying to estimate figure out a graphical model, I mean, maybe this isn't exactly the right context, but that if you already know the sparsity pattern, it's a lot easier. And I feel like people just do it like with least squares or something like that. I guess I'm wondering what, if there's any reason that you couldn't do that in this situation, or whether the MLE would help you solve something that you couldn't otherwise solve.
Okay, yeah, thanks a lot. Thanks a lot for your question. So, I mean, we're in this Gaussian setting, so the maximum likelihood estimator will be the same as the least squares estimator. So maybe, yeah, I'll go back just to this algorithm here, although it's really a linear algebra argument. So the RDAG setting imposes that certain vertices in the graph have to have the same variance, and that certain edges have to have the same weight on them. So it's a restricted model of a usual DAG model that imposes this structure, and the motivation is that it is applicable in settings where you may not have enough samples for your MLE to exist if you don't assign colors to the vertices and edges. So another thing we worked on in this project, which I didn't talk about too much today, is on these maximum likelihood thresholds. So how many samples you need for existence and uniqueness of the MLE for these models. But to get maybe more back to your question, another approach to studying graphs and dependencies between different variables could be to look at regularizing, so penalizing certain entries of the matrix to drive them to 0, and also penalizing certain differences between entries of the matrix to penalize them to have the same weight assigned to them. So that's sort of looking at these models from a model selection point of view, and here we're looking at them from a maximum likelihood estimation point of view when the model has already been fixed in advance.
Okay, thanks.
All right, are there any other questions? How about online? Okay, wonderful. Well, let's thank Anna again.
Thanks a lot.